Greetings to you, dear colleagues. My name is Vitalii Peshko, and I would like to present you a report on a scientific research extension of the operating time of high-speed turbines of nuclear power plants. The list of authors of this work is given below. Let's talk about the relevance of this research. Nuclear power plants of Ukraine produces about half of the total electricity production. The almost complete exhausting of service lifetime of power equipment and deficiency of organic fuel at the thermal power plants determines the significant role of nuclear power plants in the energy sector of Ukraine. Extending the operating time of nuclear power plant units after the exhaustion of park service lifetime is one of the most effective ways of replacing generating capacities. But it must be provided that the standards of nuclear and radiation safety are met. At the same time, the specific financial costs for meeting the requirements of regulatory documents which provide the possibility of obtaining a license for operation of power units are much less than the cost of building new power units. Usually, when extending the operation of power units of nuclear power plants, the main attention is paid to the reactor and its auxiliary equipment. At the same time, turbine equipment is under heavy load and also requires computational studies of the residual service lifetime. The purpose of this work is to develop an approach to establishing the possibility of extending the service life of the steam turbine equipment of nuclear power plants. To achieve this purpose, the following objectives were solved in the work. A calculated study of the thermal and stress-strain state of the high-pressure rotor of the K1000 turbine, determination of resistance of base metal to accumulation of low-cycle fatigue and exhaustion of long-term strands, assessment of the possibility of extending the service life of a high-speed turbine of a nuclear power plant on the example of third unit of Rivne nuclear power plant. Research on the residual service life of energy equipment is usually performed for its most highly loaded parts. The most intense loaded areas of high-speed steam turbines are their rotating elements. So the object of research in this work is the high-pressure rotor, since it is made of expensive high-alloy steel, 30 chromium, nickel 3, molybdenum 1, vanadium, and operates at the highest temperatures and pressures. The main forces affecting the stress-strain state of the rotor are stresses from temperature expansions, irregularities of temperature fields, centrifugal forces, and stresses from the steam pressure. So this photo shows the K1000 turbine at the installation stage. In the center we can see a high-pressure cylinder, and symmetrical on both sides of it are low-pressure cylinders. In order to assess the level of stresses of steam rotor for typical operating conditions, it is necessary to study its thermal state. For this, the conditions of thermal conductivity are studied in a stationary and non-stationary setting for constant and basic variable operating modes. Here is the dependence for calculating the thermal conductivity in the metal of the rotor. A convenient method for solving this kind of mathematical physics problems is to discretize the object of calculation using the finite element method. For complex designs of a high-pressure rotor, the geometric model is built in the three-dimensional mode, with account of the main elements, such as turbine stage disks, diaphragm seals, front-end seals, blade lock mounting, discharge openings, and others. The model is built using specification drawing of the K1000 turbine, and since the high-pressure rotor is symmetrical, to simplify the solution of the heat conduction tasks, it was decided to consider only half of the rotor from the steam inlet to the last chamber of the end seals. So the research model includes areas which usually have maximum temperature gradients and stress intensities. In solving the problem of thermal conductivity, the boundary conditions of heat exchange were set in all typical areas calculated by the authors earlier. Based on the calculation of the basic thermo and hydrodynamic parameters of the flow part for normal and transient operating modes, The values of temperatures, heat transfer coefficients, and heat flux density were determined for all surfaces of the geometric model. More details about calculations of boundary conditions are mentioned in this paper. So, here presented an example of the calculation of the thermal state of a turbine rotor at an electric load of 1000 megawatts. So, as we can see, the metal temperature decreases evenly from 270 Celsius degrees in the first stage to 166 Celsius degrees in the fifth stage. The temperature level in the area of the front end seals is 83 till 145 Celsius degrees. The strain stress state was estimated in a plastic elastic formulation. The highest level of stress intensity is observed in the area of the axial opening of the turbine and amounts 158 megapascals. This circumstance is due to the fact that the iterated loaded when the transients are over and the temperature field of the turbine is stabilized, the main tensile force of the rotor is exerted by the centrifugal force. Moreover, more massive stages are loaded with higher forces. Quite high stresses are also observed in the area of discharge openings and fillets of all 5 stages. In the computational study of the thermal state of the rotor in variable modes of operation, a great interest is the dynamics of changes in the unevenness of the temperature field. The jumps in temperature gradients make it possible to establish time instants at which heat shocks affect a metal. Accordingly, at these moments of the time, the efforts of the unevenness of the temperature field are the largest. So in this figure we can see dynamics of variation of irregularity of the rotor temperature field at startup from the hot state of metal, which means that at the beginning of the startup, the temperature of the metal of the first stage is nearly 150 Celsius degrees. Maximum values of the temperature gradient are observed at the rotor push, estimated time 800 seconds, and for the blade lock mounting of the first stage. The value of this temperature gradient is close to 1600 Kelvin degrees per meter, and also the following local maximums of the temperature gradients are observed at the time point of 3200 seconds, which means of 400 megawatt of electrical power, and at the end of startup mode at the time point of 14,000 seconds, when the power output of 1000 megawatts. Also, the significant temperature gradient is observed throughout all the hot startup at the front fillet of the first stage. With the end of the startup mode, the values of the temperature gradients decrease in all studied areas. When assessing the resistance of the base metal to the accumulation of low cycle fatigue, it is necessary to have information about the change in stress intensity over the cycle. When starting from a hot state of metal, the highest values of stresses, 207 megapascals, are observed at the axial opening of the turbine. At this time of the 66 seconds when the turbine is held at 750 megawatt capacity. The highest compression stresses, minus 182 megapascals, are observed at the front fillet of the first stage at the time of 3200 seconds. In this moment, turbine is ramped up 400 megawatts. At the end of the startup period, the intensity of stresses in all examined regions gradually decreases to the values corresponding at the nominal operation mode, which we saw on the diagram earlier. Similar data were obtained for all other typical operating modes of the steam turbine type K1000, and the results of numerical research of thermal and stress strain states of high pressure rotor are presented in these walks. Let's talk now about the research of resource indicators. A comprehensive scheme for calculating of the resource indicators of rotors of steam turbines of thermal power plants is described in this walk. Such studies provide for the implementation of calculations in accordance with some regulatory documents like this one. Thus, the permissible number of startups from various thermal states is estimated using experimental low cycle fatigue curves, and the strain intensity amplitude reduced to a symmetrical loading cycle and other parameters. A key feature of the calculation model of high-pressure rotor of K1000 turbine is that there are no experimental curves of low cycle fatigue for steel grade 30 chromium in regulatory documents or other literature. So, it is proposed to calculate the permissible number of cycles according to the correlational dependencies of low cycle fatigue, which you can see on this slide. A model for estimating low cycle fatigue indicators using correlational dependencies is presented in detail in this paper. The studies carried out made it possible to establish the degree of resistance of the turbine base metal to the accumulation of the low cycle fatigue and the exhaustion of long-term strength. To calculate the resource indicators and determine the possibility of extension of the operating time, it is proposed to consider a high-speed turbine of the third unit of Rivne nuclear power plant. This power unit was commissioned in 1986. As of October 2019, its operating time is 216,000 hours, with a total number of launches of 271. The results of calculating the resource indicators in tabular form are presented in this slide. As you can see, the cyclic damage accumulated in the metal is 11%. Static damage is calculated for two options. In the first case, the permissible operating time of the metal corresponds to the park resource of the K1000 turbine. Then the static damage becomes high and the total damage exceeds the limit value of 100%. In this case, the residual service life of the turbine is exhausted. In the second case, the permissible operating time of the metal was determined by the experimental curves of long-term strengths, according to a regulatory document. This value is determined by the maximum stress intensity at the rated operating mode for the long-term strength curve, which corresponds to a 99% of non-fracture probability. In this case, the residual service life of the high-pressure rotor is 26,000 hours. The study made it possible to establish that the accumulation of low cycle fatigue is not the dominant mechanism of damage for the base metal. This is due to the fact that the power units of nuclear power plants operate in the base part of the schedule of electrical loads, and they rarely operate in variable modes. In this case, the starting mode themselves takes a long time, allowing to achieve a uniform heating of the rotor, which leads to a decrease in the amplitudes of the strain intensity and also increase the permissible number of startup cycles. Since exhaustion of long-term strength is the most significant factor in the accumulation of damage, a series of studies of aging and exhaustion of long-term strengths over the entire range of operating temperatures is recommended for this steel. And finally, let's highlight the main conclusions of the research. After the estimated resource of nuclear power units has been exhausted, along with the calculations to justify the possibility of extending of the operation of reactors, similar calculations should be made for turbine equipment. A model for determining the resource indicators of the rotors of high-speed turbines of nuclear power plants is presented. It includes a calculation study of thermal and stress strain state for the most typical operating conditions. In the course of the research, it was found that at the nominal operating mode, the highest stresses arise in the area of the axial opening, as well as in the fillets and discharge openings of the turbine stages. In variable operating modes, the amplitude of the stress intensity does not reach the high values in the studied areas. The accumulated low cycle fatigue in the base metal is 11% and static damage is 78%. The residual service life of the high-pressure rotor of the K1000 turbine of third power unit of the Rivne nuclear power plant is 26,000 hours, which allows to extend the operation time of the turbine until the next preventive maintenance. Thank you for your attention.